All right, so now that we understand limits, we're going to begin to apply them when it comes to computing what we call tangent lines or slopes of tangent lines specifically. So the derivative is nothing more than attempting to find what we call the slope of a tangent line. And a tangent line is a line that will just graze a curve at a point. So take a look at this red curve here, right? We'll call this f of x. This would be a tangent line. The blue line here is the tangent line to this point. So what it does, what a tangent line does, is it sort of just glances, just touches the curve at exactly one point, okay, at exactly one point here of the curve, and then continues along. So the tangent line for a curve at this point here would look like something like this, roughly. Around here, the tangent line is going to look something like this. It is just touching the curve. It does not pass through it at more than one point. So that's what we mean by tangent line. Now, here's the tricky thing is, we know how to calculate slope, but slopes require 2 points, right? 2 points to calculate a slope. We've never calculated a slope with just 1 point. We need 2 points to calculate a slope. And so now this is where the limit idea has to come into play. So how are we going to go about figuring out the slope of that line? And if you think about it long enough, if you considered long enough, you might say like, well, if you really asked me to do it and I knew the equation for this function, I might just take 2 points very close to each other. I might say like take this point and this point, draw a line between them, and calculate the slope of those 2 points. And you say that would be pretty close. It would be exactly the tangent line, but maybe it's like pretty close. Like say that green line I just drew between those 2 points, pretty close to that blue line, right? So that would be a good way to approximate the slope. You might just take 2 points and then say, I'm going to connect them, and then that will be the slope that we'll use to approximate. And you can imagine if those 2 points were closer together, it would be more accurate. Like this is more accurate picking these 2 points than to say pick this point and say this point, and I draw a line. It's not going to be as accurate. So the closer the 2 points are, then the more accurate the slope is going to be. And that's exactly what we're going to do. Okay, we're going to now take a look. This is the first definition. This is a definition of the derivative. We use this prime notation. You can also use another notation, which is called dy dx. This is sort of like to describe a slope. Both of these describe the same thing. It is to say, what is the slope of the tangent line at a point or at a particular value? And this is the most common definition. Now, we're going to split up the limit definition. So the first thing we do, and just so you understand what this definition is, because it's a formula. I don't want you to just memorize the formula. I want you to understand what the formula represents. So what it represents here is to say, suppose I want the slope of the tangent line here, right, at this point here. I'm going to take another point that's a distance h away in the x direction. Okay, so this distance is h. And so the x coordinate, so if this coordinate is x, this x coordinate is going to be x plus h. And that means the y coordinate of this point is f of x plus h. It's just evaluating the function at this x coordinate would be the y value here. And evaluating the x coordinate here would give you the y value there, right? So there's 2 points. And then the slope between those 2 points is going to be the difference in the y value, right? So it's going to be f of x plus h minus f of x. That's the difference in the y value from this point and this point, divided by the difference in the x point from here and here. That would be x plus h minus the x value there, x. Those x's will cancel, and we get what this is sometimes called, if some of you have learned this in pre-calculus, this is called our difference quotient. Okay, you don't need to know that term for calculus, but that is, I've heard that term before if you've used it. So this is representing the slope. We call this a slope of a secant line. This is a slope of a secant line. A secant line goes through 2 points on a curve, right? So then we're going to say, this is the part we had to learn Unit 1 for. This is the entire purpose of learning Unit 1, is just so to say, like, look, I want to see what happens when h approaches 0. I want to take this value, bring it closer and closer and closer, bring those 2 points closer together, and what that approaches, whatever slope that approaches will be the slope of the tangent line. Okay? So that's the main idea of that limit definition there. It's taking 2 points, taking it as approaching 0. Now, there's another definition of the derivative, part 2. This is very similar. It's just using different variables. This is used. Why do we use this one? For one, I don't use this one very often, but it is used to compute the derivative at a specific point. Okay, and so that's commonly done. And so the way we're going to handle that is think of this point as A and this point as X. And again, we're doing the same thing. The y, if this is the x coordinate, the y value is f of x. If the x coordinate is a, the y value is f of a. And again, I want the slope at a. So the slope between those 2 points is going to be the difference in the y values, all right, divided by the difference in the x values. Okay, so that, again, that's our slope of a secant line. And then we say we want x to approach a. Okay, we want the x, again, same idea. We want to bring those 2 points closer together. So I want x to be approaching a from the right and the left side, by the way. It's not like on this picture, it's just from the right side, but we could be coming from the left side as well. So the limit is x approaches a of this thing. Both will give you, this will give you the derivative at a particular point a. This will give you the derivative in general as a function of x, and then you could plug in the point later if you wanted to. So let's kind of like see how these limits work in action, okay? So use the definition derivative, compute the derivative given the function, f of x here, and compute f prime at 2. So first, let's compute f prime of x with our limit definition. It's the limit as h goes to 0 of f of x plus h minus f of x over h. Now, all we're going to do here is compute what those things are. Now, f of x is x squared, so the x plus h, when I plug it into there, is going to be x plus h squared. F of x is x squared divided by h, okay? Now, you might, doing our limit calculations, you might plug in h equals 0, you'll just get 0 over 0. So whenever we get 0 over 0, we have to do some algebra, right? And the most natural thing to do here is let's just FOIL that thing out. Let's expand out the numerator, get x squared plus 2xh plus h squared minus x squared, right? If you don't remember how to do the binomial expansion, right? Like just look that up, how to expand out. And notice here the x squareds will cancel. X squared minus x squared is 0. And notice you'll be able to, if you do this correctly, you'll always be able to factor out an h. So you see there's an h in both of those. That's going to leave me with 2x plus h. That's because h times 2x will be 2xh. H times h is h squared divided by h. Then these h's will cancel, right? And then we're just doing the limit as h goes to 0 of 2x plus h. Now we can just plug in h equals 0 and we get 2x. So this would say our derivative is 2x, like that. Okay, that's our notation. Now, what's f prime at 2? F prime at 2 is we're just going to plug 2 into here, right? Right, because the f prime is just indicating it's another function. Another function, if x is 2, it's going to be 2 times 2, which is 4. Okay, so f prime of 2 is equal to 4 here. Now, we can also use that alternative definition to say if I wanted to just do that straight up, I could just say, oh, I want the limit as x approaches 2, right? So I'm going to write out the definition again. It's going to be f of x minus f of a over x minus a. That was equal to the derivative at a. So let's just plug in 2 into here. So this is an alternative way using the other definitional form. It give you the same thing. F prime at 2 is going to be the limit. We just replace a with 2. F of x minus f of 2 over x minus 2. All I did was replace a with 2 because that's a is where I'm computing the derivative at. Okay, now what's f of x? F of x is x squared. So we're going to do the limit x approaches 2. This is going to be x squared. What's f of 2? Plug 2 into here. 2 squared is 4. Minus 4 over x minus 2. Notice this looks very similar to what we did in Unit 1, which is one of the reasons you could use this one, because it looks very similar to the kind of limits we did previously. This one we factor, right? X plus 2, x minus 2 over x minus 2. That'll cancel. And then plug 2 into there, we get 4. Now, the downside of this one is it only gives you the derivative at a specific point. This method is more robust because it gives you, you can now compute the derivative at any point. Because if I want to do f prime at 3, I know it's going to be 6. Whereas this one, I would have to redo it again with a is equal to 3. Okay, so this is a less useful form, but you still are expected to know it for the AP Calculus material. Okay, let's do another example with a different variation. Let's compute this one. So use the definition of the derivative. So we'll do the limit as h approaches 0. I like to just write the definition again each time, just to remind myself. Writing down the equation each time will help you remember equations. If you struggle to remember equations, then writing them down every time you invoke them will help you remember it. So this would be 1 over x plus h, because plugging x plus h into here and then plugging x into there is just 1 over x over h. Now this one, you might say like, well, that one is, I can't just FOIL it out or anything like that. Here, when you have fractions, we want to do common denominator, right? So what would be the common denominator of these two? Is I want x on this one, x times x plus h. In here, I'm going to need an x plus h and x plus h. That way, these two will have both a common denominator, x times x plus h, right? And I'm only just multiplying by 1 because I got to multiply the numerator by the same value as the denominator. So it's going to be x over x times x plus h minus x plus h over x times x plus h all over h. Now, you have to be very careful here. You are subtracting this entire thing. It's this numerator is going to be x minus x plus h, and that's going to give you negative h. Okay, so be careful because you're subtracting this whole thing. So it's going to be negative h over x times x plus h. And instead of dividing by h, taking this, I mean, you could say over h, but I could just make it multiplying by 1 over the reciprocal, right? Because dividing by a fraction is multiplying by the reciprocal, right? And then you see now the h's cancel. And now I can plug in 0, right? So it's going to be negative 1 over, for h I'm plugging in 0 over x squared, right? Like that. And therefore, f prime at 1/2 is going to be negative 1 over 1/2 squared. Just going to plug that value in. That's negative 1 over 1/4, which is negative 4, right? Dividing by fractions, multiplying by the reciprocal. And again, if you want to use the other alternative definition, we'll do the limit as x approaches 1/2 of f of x minus f of 1/2 over x minus 1/2. This is the other form. This would give you f prime at 1/2. This is if you want to compute the derivative at a specific point, then we would do this, right? So the limit as x approaches 1/2, f of x is 1 over x, f of 1/2 is 1 over 1/2, which is going to be 2 over x minus 1/2. Again, this is not my favorite form, but this is just good practice. So this is 1 over x minus 2 over x minus 1/2. Now, again, when you have fractions like this, it's very common to just say like, oh, I want to, make them the same common denominator. So make this x over x as an example, right? So that way we have a 1 over x. So then this would be the limit x approaches 1/2. This would be 1 minus 2x over x minus 1/2. And this one's a little bit trickier to see, but we want to try to cancel out this we want to make this one look like this because we need to do some kind of canceling, right? Ultimately, you have to cancel. And the 1 minus 2x, you have to recognize, there's a couple ways to do this. You could just multiply this by 2, like multiply the denominator by 2 and the numerator by 2, or you can think of this as like, oh, I can factor out an x, or not factor in x, factor out a 2 just to make it x, and then this would be 1/2 minus x. Or if you factor out a negative 2 or multiply by negative 1, then it would be negative 1/2 plus x, right? And that would be x minus 1/2. So then this guy becomes the limit as x goes. This one's a little trickier to see. This is why I don't like this method. It requires some tricky manipulations to get it to work. And then we're dividing by x minus 1/2. And then you can see this will cancel. And so we have negative 2 over x, and then we can plug in 1/2. So it's negative 2 over 1/2, which is going to be negative 4. So a lot longer to get us there versus the straightforward method. Okay, let's take a look at another one. Use the definition of the derivative to compute. Same thing. Limit as h approaches 0, f of x plus h minus f of x over h. That's going to be the limit as h approaches 0. So when we plug in x plus h into there, it's going to be 1 over square root of x plus h minus 1. This one, f of x, is going to be 1 over square root of x minus 1, and then all of that divided by h. Now, this is going to be a combination of things. One, we're going to have to do common denominator, right, to make them the same, to combine the two fractions. So we'll do this x minus 1 over root x minus 1, and this would be square root of x plus h minus 1 over square root of x plus h minus 1. That way the denominators will be x minus 1 times that. So then this will be the limit. H goes to 0. This will be square root of x minus 1. And let's just combine the numerators because we know they'll have the same denominator. Divided by the product of these two. And don't necessarily expand it out because I only want to do some things. And then rather than writing as dividing by h, I'm just going to multiply by 1 over h, right? Because that way it's not so tall when I'm writing it out. Okay, so then you might say like, okay, cool. I'm still getting 0 over 0. So how do we handle this portion of here? This is where we're going to use conjugates. Okay, square root of x minus 1 plus the square root of x plus h minus 1. And we got to multiply the denominator by the same thing. Now, why do we do this? Why is this helpful? Well, the reason, it's just like we did the limits before. We do the conjugates because when we FOIL them out, it will get rid of the square roots and it will allow us to factor and simplify things. Oops, switch to blue instead of black. So root x minus 1 times root x minus 1 is going to be x minus 1. Then the inner terms will cancel because that's what difference of squares does when you're doing that. And then it's going to be minus this times this, which is going to be x plus h minus 1. And I would strongly recommend you put parentheses so you don't forget to distribute the negative sign. And now the denominator is tricky. There's an h. There's a square root of x minus 1. Don't FOIL this part out yet because we're just... Remember, our goal is to cancel out this h. So we're doing manipulations here so we can cancel this h out. And then this is going to be root x minus 1 plus root x plus h minus 1. You can see how tedious it's getting for a relatively simple function to find. Okay, so this one's going to be, you're going to subtract. It's going to be x minus x. That will cancel. And then minus 1 minus minus 1. So that will cancel. So we're just left with negative h on the numerator. And that will cancel, and we were left with just negative 1 on the numerator. Okay? And that's what we wanted. Because we got to cancel the h on the denominator, because that's what's making the denominator 0 for our 0 over 0 kind of situation. Right? So then as x, then we plug in 0 into here for h. So this would be square root of x minus 1, square root of x minus 1, because this will be 0. Then this will be square root of x minus 1 plus square root of x minus 1, because this h is 0. So that times that is going to give you negative 1 over, this will be x minus 1, and then this will be 2 square roots of x minus 1, because you have 2 of them there. So you can leave it like that. That's fine. That's the calculus portion. You can simplify. And now we want to compute at 5. Right? Negative 1 over 5 minus 1 is 4 times 2 times square root of 4. And that's going to be 2 times 2 is 4. 4 times 4 is 16. Negative 1 over 16. Like that. And I won't do it the other way for this one because I think it would also be pretty tedious. But you would do a similar technique of using the conjugate to complete the derivative. Okay. Thanks for checking out this video. I hope you found it really helpful. If you'd like more support, maybe you need more multiple choice practice, maybe you just need more guidance and things like that, I have plenty of information on my website. If you look in the description below and go to www.bothellstemcoach.com, I will explain all the ways I help students be successful in their AP classes.